What is this paper? So it's called a Gaussian integral formula for the Hermite polynomials, Combinatorics, Asymptotics, and applications, and I'll give you a quote from the abstract. This article is primarily expository and features many illustrative figures. Here are some of the figures. This is, you know what, nowadays when you watch a trailer, they don't just show you the trailer. The first couple seconds of the trailer are like the trailer to the trailer. These are the figures of the trailer to the trailer. We'll do these in the talk. But basically, we were working on something. I'll mention it when we get to it. And we discovered this nice formula for the Hermite polynomials that, if you're a probabilist, just makes everything way easier and way nicer. And it explains all these things. And I'd worked with the Hermite polynomials before, and they were always kind of annoying. And now I feel like I finally get them. And so we wanted to share that with the world. This is a quote from William Thurston that I really like. Mathematics is not about numbers, equations, computations, or algorithms. It is about understanding. And so, the Hermite polynomials are a super old topic. But I feel like I've understood them in a way that I want to share with everybody. So that's why we're doing this. Okay, first of all, what are the Hermite polynomials? Let's get that for people who have never seen it before. So there's some sequence of polynomials. Here's the first few. 1, then x, then x squared minus 1, then x cubed minus 3x. Here's some graph of them. What's the definition? They are the monic polynomials, so they always start with x to the n. And they are orthogonal with respect to integration against the Gaussian density. So they satisfy this equation. If you integrate the mth one with the mth one, you should get 0 if n is not equal to m. It turns out you get n factorial if n equals m. Hopefully, if I have time at the end of the talk, I'll explain why it's n factorial and not some other number. But this is the definition. You want them to be 0 if n is not equal to m. You could get them by Gram-Schmidt on this set of polynomials. That's what they are. What's the point of all this? Why are we doing this? So part 3 of the paper, but part 1 of the trailer to the paper, is applications. Why do we care about the Hermite polynomials? I'm going to show you the cool stuff first, and then I'll talk about how we actually do it. And the application I'm going to talk about today is Dyson Brownian motion, also known as non-intersecting Brownian motion. Okay, what is not today? So again, this is the trailer. So not today, here are some other applications in the paper. One is the quantum harmonic oscillator converges to the classical harmonic oscillator. When I first saw the Hermite polynomials, I was in like a 3rd year quantum physics class, and the Hermite polynomials appear in the location of a quantum particle with the nth lowest possible energy. And if you take the limit as h bar goes to 0, so if Planck constant gets really small, then quantum physics converges to classical physics, and you have convergence of the Hermite polynomials to the arc-sine law. This is a classical thing, but nobody wrote this down. So if you open the quantum books, they all point to each other, and they point to some paper from the 70s that's incredibly hard to read. So we finally have a nice proof. I really like this picture. So the quantum oscillator goes up and down, and it converges weakly to the arc-sine law. And then another one is Edgeworth expansions. If you have a sum of random variables, the central limit theorem tells you the distribution will be Gaussian. But what is the correction to the Gaussian? That is the Edgeworth expansion. It involves the Hermite polynomials. Actually, this is the application that brought Janos and I to this paper. We were working on a multivariable Edgeworth expansion. We needed for some understanding some large neural networks very precisely. There was no technology for this. We kept working out stuff, and these weird miracles would happen. We're wait a second, there's this easy formula that does everything. So this application is really what caused the whole thing. But today I'll talk about Dyson Brownian motion. Okay, what is Dyson Brownian motion? Here's the simplest possible explanation. Imagine you have 2 Brownian motions. So I call them x1 and x2, but they are coupled in that they push each other. So you have this difference 1 over x1 minus x2. That is how far apart they are. And they push each other in that way. So x1 is getting pushed upwards by x2, and x2 is getting pushed downward by x1. But they're both Brownian motions. If you run it, it looks something like this. So there's the red particle and the purple particle, and they're both doing their Brownian motion stuff, but they push each other. That's n equals 2, so they push each other. What's the exciting thing to do, of course, is to take n larger and larger. So here there's 5 of them, and they all push on each other. So every particle pushes on every other particle with this difference 1 over their difference in position. Here's what it looks like with 5. Okay, so the top one is getting pushed way up because there's 4 people pushing the red guy up. The purple one gets pushed way down. There's 4 people pushing the red one down. But the green one in the middle, he's sort of getting equally pushed from the top and the bottom, so he stays in the middle. This starts to have some cool patterns. So here's n equals 16. 16 of them. And you can start to see some nice patterns emerging. So one thing is, because they all start together, they very quickly push apart. So you sort of have this asymptotic infinity slope over here. And you might also notice, if you look very carefully, is that they're more crammed together in the middle. So the ones in the middle sort of tend to be closer together than the ones on the outside because they have more pushing going on. So the interesting thing to say is, what happens if n gets larger and larger, right? What happens in the limit n goes to infinity? And that is exactly what you can do with the Hermite polynomials. So you can actually write down the exact law for any n in terms of the Hermite polynomials. So you have this, you do this crazy product, the kth Hermite polynomial of x times the kth Hermite polynomial of y. You add them up and you scale it by some stuff. This gives you something called we call the Hermite kernel. And this tells you the exact law of anything you would want to know about that picture that I just had. And in particular, you can prove lots of nice limit theorems. So one thing is if you ask, okay, where are the particles at some fixed time t? So you do a big slice at time t equals 1. You say, where are the particles? You get this gray curve, which is the exact position. This is for n equals 16 is plotted here. So exactly what I had in the rainbow a second ago. And you can see there's a lot of particles in the middle. You can actually see where they're likely to be, and they're very likely to be in certain spots. But you can also see the overall limit shape is the semicircle law. And this also comes from random matrices. Dyson Brownian motion is also really connected to random matrices in a certain way. All of this is explained in the paper. All of these are screenshots from the paper, by the way. So if you want to see more about the figure, you can get it there. So the limit is the semicircle law of this thing, and we have a nice proof that's very satisfying. Why is it a semicircle law? Starting from this that I'm very happy with. But we can also prove more complicated things. So for example, the top particle is very interesting. The top particle is exactly the last passage time in the setting of the previous talks. And we can prove Tracy-Whittem fluctuations for where the top particle is. So this is a 90% confidence interval is shaded in red here for where the top particle will be. And the limit shape is this nice quadratic. And we have the fluctuations around it. This is the kind of thing that you can use to prove the directed landscape. So you can take this model as your starting point, take the limit in the right way, and if you actually do the joint distribution, which is a little more complicated than what we did here, you will get the directed landscape and the KBZ fixed point. Okay, here is the bonus thing. I think this one is genuinely new. So imagine you have the exact same setup as before, but now one particle starts very far away from the other ones. So before they were all starting at 0, all the Brownian motions. But now the red Brownian motion, he starts a little bit higher up, okay? And this one actually you can kind of think of this as a signal to noise situation. If in actual life, you're trying to measure something that has 36 variables, and maybe there's like one direction that is the thing you actually want to measure, and there's like kind of 35 noise directions that are just pure noise, this is kind of a model for that. So you have one thing you're trying to measure, but there's all these other like annoying things that you'll see as I add noise, will sort of get in the way of measuring the signal that you want. Okay, so that's the setup. And the question is, what's going to happen when I hit play? So we're going to animate the same thing, same exact rule, same Brownian motion. They push each other in the same way. What happens? Here it is. Okay. So the cool thing is, first of all, the 35 particles down here are doing the same thing they were before, essentially. That's because there's only one person above them. They really are not highly affected by this guy because there's only one of him and there's 35 of these guys. So they don't really care about that. The guy on the top, though, has something interesting. So first of all, he travels at a slope, and that's because of the sort of bulk effect of the 35 people below. But eventually, the slope he's doing is not enough to stay away forever. Eventually, he sort of crashes into the bulk with everybody else. And by the end over here, if I had just covered up the first half, which I guess you can probably see it on my shirt. But if I had just covered up the first half, you wouldn't be able to tell the difference between this picture and the one before where they started at 0. So what's happening is there is sort of a signal, and you can watch the signal for a while, but eventually the signal will crash into the bulk, and the signal will be gone. So the signal to noise ratio determines how far you are, but eventually the noise overwhelms the signal, and you can't tell what's going on anymore. And this happens very suddenly. So we prove a nice limit theorem. This is, again, a screenshot from the paper. There's this Gaussian behavior regime before the phase transition where the top particle is separated from the bulk, and you can really figure out where it is, and it has these Gaussian fluctuations. It's like all the regular math. And then it has this other regime where it's kind of indistinguishable from this setting where you start at 0. And it has Tracy-Whittem behavior and so on. And again, this goes by some explicit computation with the Hermite polynomials. We write down the exact kernel. So it's some nasty kernel. It's the kernel from before plus some other stuff involving the Hermite polynomials. And then you just like control which one is big where. So in the blue regime, the new stuff is the big thing. And then in the red regime, the old stuff is the big thing. And one of them is much bigger than the other. So it's some really nice analysis. Some people in other models, this kind of thing is called the BBP phase transition. I have to say that because my PhD advisor was one of the Bs. So if I forget, I'll get in trouble. Okay, But that was a slightly different model. That was for covariance matrices. This is for Dyson Brownian motion. I think this is essentially the new result of this paper. Everything else is sort of old things proven in a different way. Yeah. Oh, with n, yeah. So this is all in the limit. So you have to take the limit as n goes to infinity, and this will happen at some square root of n. So some distance square root of n. I'm going to talk about the scaling. The asymptotics is next. So the paper is called Combinatorics, Asymptotics, and Applications, and then the trailer is called Applications, Asymptotics, and Combinatorics in reverse order. Yeah, so we'll talk about the scaling in a minute. Yeah. And if you look carefully, you'll see, there's an n over here and things like that. Yeah, good question. I will say the other cool thing, again, this is due to Ballant. You might notice that this line is tangent to the red dotted line. The blue line is tangent to the red dotted line. And you're like, whoa, why is that? And I don't have a good explanation why. You sort of calculate it and it comes out. But Ballant said, imagine you have a rubber band. You can think of the Brownian motion as minimizing the quadratic energy just like a rubber band. And if you put a rubber band on top of this red curve, then it will always be tangent. So this is a nice way to think about it as well. Yeah, so I think this is a cool thing. I'm quite happy with it. Okay, we're going to move on to the next question, which is, how do you prove these theorems? How do you do it? And we have these nice asymptotics, these limits of the Hermite polynomials. And some of this is quite old, as I'll explain. But I think our approach is new and is more intuitive. And this is my favorite figure from the whole paper. 3 approximations for the Hermite polynomials when x is order of square root of n. And there's 3 approximations here. In gray is the original Hermite polynomial. In blue is one approximation. Look at how beautiful this is. The blue is right on top of the gray. You see that? That means we got it right. Over here, the red is on top of the gray. And if you want to see the difference, you want to make sure we didn't cheat and just draw the same thing. You have to zoom in right over here on this purple line, where you see the blue actually has a little asymptote, right? It goes right off the gray, right exactly at x equals 2 square root of n. So the blue approximation is sort of bad exactly at x equals 2 square root of n, but is good less than that. The red approximation is good for x bigger than 2 square root of n, but is bad exactly at x equals 2 square root of n. But of course, there's a third approximation, which is the green. You see the green is perfect at x equals 2 square root of n. And these 3 approximations glued together kind of approximate the whole Hermite polynomial extremely well. Extremely well. This is some kind of modified log scale. So when I say they're right on top of each other, I mean they're equal up to a constant that is getting close to 1. So that's why it looks like this, goes up and down, up and down. How do we prove these things? And why are there 3? Why should there be 3? This is crazy. Why are there 3? Well, there's a simple reason. And the whole point of this paper really is that there's an old way to do this kind of thing, and then there's the new way. It turns out the old way is from exactly 100 years ago. So I thought that was fun. I had to show you. This is some French paper by these guys, Plancherel and Rota, who are famous. Whenever people talk about these asymptotics, they say the Plancherel-Rota asymptotics. This is some French paper, and they really do it the classical way. So the Hermite polynomials are some derivative definition, and then you access the derivative by doing the Cauchy integral formula. And you have residues, and you do a whole bunch of stuff, and you hit the residues, and then you figure it out. But our new way is the title of the paper. The new way is the Gaussian integral formula for the Hermite polynomials that all the probabilists will like, which says don't do derivatives. Dear God, stay away from the derivatives. The Hermite polynomial is the expected value of something involving a Gaussian random variable. And all it is you take x to the n, which would be, the monic polynomial you want, but you don't do x to the n, you do x plus I times z to the power n, where z is a standard Gaussian. And x plus I times z to the power n, that is the Hermite polynomial. It's so simple. Yeah, I guess this is simple unless you don't like expected values. If you don't like expected values, then you haven't done anything. But if you like expected values like b, you're like, oh my God, this is amazing. And this, of course, becomes an integral just by writing down the density for the Gaussian. And the advantage is, before there are these residues, there's also this annoying thing. There's an n factorial in the Cauchy integral formula, and we don't have an n factorial. And so our final answer doesn't involve n factorial. If you look up the Plancherel-Rota asymptotics online, it says big formula times n factorial, and then you have to do another round of asymptotics with the n factorial, but ours doesn't have that. It's just straight out. And of course they're equivalent because they're both what the Hermite polynomials are. But I really think ours is nicer in some sense, and it's some kind of coincidence with the fact that the Gaussian is its own Fourier transform. That's what makes this work. It's not some simple. You can't just rejig this unless at some point you use the fact that I just said. So it's some kind of cool thing. Okay, well, why does this help us? If you're good at asymptotics of integrals, you look at this and you go, I see. But let me tell you how to do it. So here is the asymptotics when x is a constant times root n. And so what you do is you write the integral, which before is something plus I times e to the minus z squared. And you say, hey, something to the power n. It would be so nice if there was also a power n in the e to the minus 1/2 z squared, because then everything would be to the power n, and that would be nice. And so what you do is you do a change of variables where you replace z with square root of n times w. And then that puts an n in the exponent, okay? And when you put an n in the exponent, now everything is something to the power n. So this crazy integral is just some function. It's e to the n times some function. And I have like sort of cleaved the dependence on n and a completely in two. There's the dependence on n on the outside. And then there's just this nice function f that's like chilling and there. And then when you take the limit, you're just worried about where is the value of f the largest. You see, because you have e to the n times something. And when n is like a quadrillion, then f, the only thing that matters is where f is really close to its maximum. That's the only thing that matters. And what is the function f? It's not too nasty. It's the log of a plus I over 2w minus w squared. The minus w2 squared comes from the Gaussian part, and then the I over 2 comes from this part. And this is where you can really see the three cases in the approximation. So the three cases come from looking for the critical points of f, and the critical points of f are a quadratic equation. So there's three cases. In the same way, when you were in 10th grade, they said, please write down the three cases for this quadratic equation. It's exactly the same three cases, okay? Here are two of the cases. You either have two roots that are sort of horizontally to each other, or you have two roots that are perpendicularly to each other. This is on the imaginary plane. So it's either plus minus I times something or plus minus something, right? You do the quadratic equation, the two roots are either left, right of each other or up, down of each other. There's a hidden third case, of course, between these, and that is when the roots are exactly equal, if you have a repeated root. And this is the edge case. And in this situation, you have a double critical point, so that not only is the derivative 0, the second derivative is 0, and this is what causes things to be different. This is what causes the end of the 1/3 in the KPC universality class. So the picture I had before is really these three cases. The blue is the case over here with two roots to the left of each other. The red is the case with two roots above each other. You only need to look at one root when you sort of deform the r axis. But the interesting thing that the KPZ is this double critical point of this function, where you have, because the function has two derivatives that are 0, it's sort of you need to use an extra term in the Taylor series approximation, and that's why you get this airy stuff. And you can kind of see the airy function. If you know the airy function, it wiggles and then it is flat. There's the wiggles and the flat. Okay, that's asymptotics. How much time do I have left? Couple of minutes. Okay, great. This is perfect. So I prepared for this. The last bit is combinatorics, which is really just for fun. And I was suspecting I'd be low on time. So I'm going to explain to you how I explain the combinatorics. Actually, I always feel like this when I'm doing combinatorics, because it's sort of like really easy to say, but then the proof is like longer and harder. So I'll just tell you in a couple minutes. So what are the combinatorics? You start with the Wick theorem for the expected values of mean zero Gaussian. So here's the expected value of a product z1 times z2 times z3 times z4. It's a sum over you pair up the four things. You can do all the possible pairings. Here it is with 6 things, all the possible pairings. That's the Wick theorem. You get facts like this. Like, for example, the expected value of z to the 4 is 3 because there's 3 pairings. The expected value of z to the 6 is 15 because there's 15 pairings. But in general, you can calculate all of these by writing these crazy diagrams with lots of pairings. Mihai from the future here. Just wanted to quickly mention, if you've never seen anything like these weird pairings before, I made a video for the Summer of Math Exposition a few years ago that explains them all in detail and how they can be used to prove the central limit theorem. This video is definitely the one I've put the most amount of effort into, so if you want a place to start and you want to learn more about Gaussian random variables and what they have to do with these pairings, check that out. Okay, back to the Hermite polynomials. Okay, we can use this to calculate things. So here's a Hermite polynomial where I put in the t as the variance instead of just a 1, and you can do all these pairings. You have all these pairings. So there's an x to the 4 because you take the x's, right? You pull out the x's here. You pick x 4 times. If you pick out 2 x's and 2 copies of itz, you get a minus because it's I squared, see? And then you get a t from the square root of t squared. And then there's 2 copies of x's. So you get a x to the 4 minus 6tx squared from the one diagram like this, 6 diagrams like this. And there's 3 diagrams where you pick t times z 4 times, but there's 3 pairings to do it. So by doing this, you can write down all the terms in the Hermite polynomial. Those 3's and 6's, they actually make combinatorial sense. And the minuses come up because there's i's in there, right? It's I squared is minus 1. You can use this to prove orthogonality. This is my favorite proof. in the paper, you can prove that the Hermite polynomials defined like this are orthogonal. And then the proof goes something like this. Here's an example when you have 3 and 3. You have this integral. You write the integral as an expected value over 3 Gaussians. You have the x, which is this big integral. You have the L and the R from the formula. And you have to calculate this Gaussian expectation. And this Gaussian expectation is the sum of all these crazy diagrams that look like this. Here are some of them. But then there's a nice function called tau that swaps the L's with the X's. So you swap the L's with the X's. When you swap the L's with the X's, you get a minus sign. That's because you went from IL to XX. And therefore, these two diagrams cancel out. So even though there's this like huge soup of diagrams, you can sort of pair them up with this function tau and say, hey, you have these like thousands of diagrams, but they all cancel out, except for the ones that look like this, that pair all x's to x's. So the only ones you got to account for are the x's to x's. How many x's to x's are there? Well, there's 3 factorial. There's 3 factorial because you have to assign every x on the left to an x on the right, and there are 3 on the left, 3 on the right. That's why there's an n factorial in this thing, which is a nice result. Okay, I'm a little over time. I will stop there. Please go read the paper if you found this interesting. Thank you.